So today, with the launch of Trainium 2, we actually also announced partnership with open source partnership with Google. We are very proud to partner with Google around JAX to enable more use cases and make sure code portability with JAX allows customers to choose the right hardware for their solution. And of course, the JAX native integration of the OpenXLA project, which I mentioned before, makes it really easy. And I hope you'll see that very soon when Matt goes on stage. There are a few other customers that are already using JAX. The Anthropic team that we talked about quite a lot today, they actually started using JAX over a year ago. And they have seen great results in moving and porting their code from the platforms they were using onto Trainium very easily because of the code portability that is built in natively into JAX. And with that, I'm very happy to invite Matt to stage. He's actually the original author of JAX, started as a skunk project within Google, and then grew to the amazing framework it is today. I'm very proud to accept to the stage Matt.
Hey, thanks, Scotty. Yeah. All right. Sound okay? All right. Yeah, so I'm Matt. I work at Google DeepMind, and I'm here to tell you just a little bit about JAX. So this is JAX in one slide. JAX is a Python library for numerical computing and especially large-scale machine learning. You can see on the left an example of JAX code for implementing just a very trivial, fully connected neural network. And you can see it looks just like writing JAX. JAX code looks just like writing NumPy code. So behind the scenes, when you write JAX NumPy functions, when you call them, JAX uses the OpenXLA stack and the XLA compiler to run those functions on CPUs, GPUs, TPUs, and now also on Trainium. And so JAX was built from the ground up to use XLA, and being able to run NumPy functions on accelerator hardware this easily would have been a dream for me in grad school, and so I'm glad that it exists now. So that's sort of the first half of JAX, is like, oh, just run NumPy on any accelerator hardware you want. That sounds pretty great already. The second half of JAX, where it really starts to shine, is to do with what we think of as function transformations, these colorful grad, JIT, and VMAT things I've highlighted here. So function transformations are things like grad for autodiff. So if you want to train your network, use autodiff. Grad is our function transformation for doing that. JIT, for just-in-time compilation, is where you can say, I want to stage out this entire function to the compiler. Not just compile individual JAX NumPy functions, but I want to stage out end-to-end the function that I wrote for my neural network prediction function or loss function or optimizer update step. And by staging out to the compiler, not only can the compiler do optimizations like deciding fusions or layout optimizations, but this is also what gives JAX the power to scale from one accelerator chip to many thousands. So people have been able to do a lot of different things with JAX. We've heard about some of them. So as you may know, Google DeepMind's all of the large language model and large multimodal model work is done with JAX. Also other companies like Anthropic and Apple Intelligence, but also like XAI on GPU, they use JAX to power a lot of their large-scale machine learning work. But there's also work on image and video generation from Google, like Imagen and Midjourney, and work from Google DeepMind on mathematical reasoning, these sort of things. So JAX helps power all these. A bit beyond standard machine learning, JAX also helps power a lot of scientific computing. So for example, AlphaFold 3 for protein prediction and Nobel Prize generation. It's also used in robotics for things like simulation on accelerators, and for things like climate modeling, large-scale climate modeling. And finally, JAX is used all over in academic research, from synthetic biology to astronomy to things like cutting-edge AI research. So how exactly does JAX help all these people, and how does it power all these things? It really comes down to that JAX gives you AGI. And by that I mean a simple composable functional API paired with the fact that it's geared towards compilation and scaling up just from the beginning, and inherent portability across all of these platforms. And to try to show you some of those things and give you a concrete taste, I'm going to attempt a live demo. Let's see if we can pull this off. All right, hey. Great. So this is a Trainium instance. It's Trainium 1 because I prepared this before this morning, but I'm excited to try this on Trainium 2. Let's just, I started this notebook. Let's just start running NumPy operations. So here we've imported JAX NumPy, and we're making a big matrix and multiplying it together and printing out some results. That's great. And you might not even know that this is running behind the scenes on a Trainium chip. But if you look, you can see that, yes, the data indeed live on Trainium neuron core here. And just using these kinds of operations, like these NumPy operations, we can start to write neural networks. So here's our toy neural network from our first slide, along with some parameter initialization code and just some synthetic random data. And we can start to run it. We can say, let's run a prediction step. Let's evaluate our loss function. So that's just running JAX NumPy on Neuron or any other platform you want. If you want to start to stage things out to really start to get performance, you can use jax.jit. That's our decorator for just-in-time compilation. You apply it to a Python callable. It gives you a new Python callable that is end-to-end stage out, the entire thing, sort of whole graph capture, if you like. So here we're running our prediction function and our loss function. And up to floating point tolerances, you can see we're computing the same numerical function. But now it's been staged out. Where JIT really starts to shine is when we do parallelization through automatic partitioning of computation. Let's take a look at that. So we were actually just running computations on one neuron core, but that's not making good use of this machine that I have running because we have 32 neuron cores available. And moreover, when you're running, you might want to scale out to hundreds or thousands of chips. So let's look at how JAX has one unified approach to expressing batch data parallelism as well as any other kind of parallelism you might like. So here's a simple batch data parallelism example. We're going to take our devices and we're going to say, let's make a mesh out of them. In this case, we're going to start with just a simple one-dimensional mesh of our 32 devices. And we're going to call that mesh of devices in a line. We're going to say, let's name that single axis the batch axis. And then we're just going to put our data, our inputs and our targets. You can think of this, our data is two-dimensional, right? And the batch axis is the leading axis. And so we're saying, take a chunk of inputs, a chunk along our batch, and give each chunk to one of these neuron cores. So this is just a simple visualization of our 2D array of data. And even though it appears like one array to JAX, we can see that it's backed by memory across all of these different devices. We've given one chunk of that data to each of these different neuron cores. And now we can do the same thing we did before. We can compute the loss function, and we can run predictions. And this is actually being parallelized for us behind the scenes. In this case, the parallelization is really simple, just batch data parallelism. But it's just happening behind the scenes with the compiler. It has to recompile for every new sharding, of course. And we can see, in this case, this is just simple batch data parallel case. Indeed, our predictions are coming out laid out in a parallel manner as well. That's just giving you some indication that indeed we are keeping the data distributed and partitioning the computation to be parallel. Let's start mixing that in with more. So here we're going to use jax.grad for autodiff to just do some training of our toy neural network. So you apply jax.grad to the loss function. That gives you a new function that computes the gradients with respect to the first argument. So if we run this, remember this is running in batch data parallel because we just made our data distributed. And you can see we get gradients out. If you think about it, actually, the compiler is doing something non-trivial here because to get the gradients, it has to automatically insert an allreduce to compute these results. But we don't have to worry about that. We just get to set the sharding, and it's being parallelized automatically for us. So here's a simple update step. This is a simple gradient descent on our parameters. We can see we're doing grad underneath our JIT, and we're just going to loop calling this many times. So this whole update step is being sent to the compiler. It can be end-to-end optimized, and we can see that now this is going to be, loss goes down. That's great. Maybe we can have a bigger step size. After all, loss keeps going down. That's great. That's AI. So I think I might skip this section. But briefly, you can even compose more JAX transformations together. This really starts to give you a lot of expressive power. In this case, we can use VMAP, which does efficient vectorized batching of computations to do things like compute per example gradients. So if you're doing some computations, for example, at differential privacy, maybe you want per example gradients, JAX makes that super easy to express. And of course, you can compose that with autodiff and with end-to-end just-in-time compilation and automatic parallelization. So as one final example, I'll just show how we can try different parallelization strategies. So in this case, we're going to take our mesh of 32 devices, and we're going to make it two-dimensional. We're going to say, I actually want to do some model parallelism, some tensor parallelism, and also do some batch data parallelism at the same time. So we're going to take our 32 devices, we're going to think of it as a 16 by 2 mesh, and then we're going to place our data so that our inputs, our input data is sharded along its batch dimension and along its feature dimension, and the input parameters are also sharded along their sort of leading feature dimension in this way. And I'm going to make one change to our example code as well, just as a hint to the compiler to say how we want to keep things sharded. I'm going to annotate this intermediate with a sharding constraint to say I want the results of my matmls to stay sharded in this way, where I'm doing both batch data parallelism and tensor parallelism. And what that changed behind the scenes, let's see what our loss value was before, 415,339 something, and now, now we're getting this result out. Now instead of just batch data parallelism, we're doing batch and model parallelism. So that's how JAX gives us one unified mechanism to do parallelism and to scale out from one chip to 32 cores in that case to many thousands. So that was just a brief introduction on JAX and why it might be useful to you. And I think with that, I'll end and hand it back to Gadi.
Thank you very much, Matt.
Thanks.
This was awesome. You guys, there is a test on the way out, just to make sure you got everything here. This was pretty awesome.